In this video, we're going to test out our model of a BJT in a circuit. This is going to be an example problem, and it's super instructional to wrestle with it for a bit, so please pause the video when asked and give the problem a try. A circuit is pictured below, and I'd like you to find the large signal IC, figure out the largest RC that you can use in this circuit and still have it be in forward active, and calculate a few small signal parameters. Pause the video and give it a try. To start solving this, I've drawn the large signal equivalent circuit in place of the BJT in this circuit over on the side. I don't usually draw large signal circuits out like this when I'm solving problems, but it's good to draw them out when you're just getting started with BJT analysis. You can see from this circuit that we're assuming the base voltage, VB, is 0.7 volts. Because it's just one VBE on above the grounded emitter. One quick note about the circuit symbol for BJTs. This little arrow in the circuit symbol tells you where the diode is in the model. You can see that we have a diode from the base to the emitter, which matches up with the little arrow between the base and the emitter. That's a handy trick to remember how PNPs work. We calculate the base current by finding the current in the 100 kilo ohm base resistor. We find the voltage across it by subtracting the base voltage from the 1.7 volt input voltage. The base voltage is 10 microamps. Because we're in forward active, IC is given by beta times IB, so IC is 1 milliamp. Note that we can't find IC until we find IB, because IC is completely determined by IB in forward active. The base sets the behavior of the collector current, and moving the collector voltage around won't change it because of this dependent current source. Also, though it doesn't matter in this problem, it's worth noting that the base current is much smaller than the collector current, in fact beta times smaller. Which means that the emitter current, which is the sum of base and collector currents, is about the same as the collector current. It's really common to approximate IE as equal to IC for hand analysis, even though IC is technically beta over beta plus 1 times IE. For a beta of around 100, that's less than 1% error. This circuit will enter saturation when the base to emitter voltage is greater than 0.7 volts, which is already true, and when the collector to emitter voltage is less than VCE sat, or 0.2 volts. So we need to find what value of RC will create 0.2 volts at the collector. Because we know IC is 1 milliamp, and the supply is 9.8 volts above 0.2 volts, we know that 9.8 kilo ohms of resistance will drive VC low enough to cause saturation, where VC is the collector voltage here. As an aside, the supply is called VCC by tradition, because it's often separated from NPN collectors by just one element. So if this is VC, you just call the nearest thing VCC. Since we know IC, it's easy to use our large signal relation to calculate GM. 1 milliamp, which is 1 milliamp divided by 25 millivolts. It turns out it's pretty convenient to round phi th to 25 millivolts instead of 26, because it gives you nice round numbers like 40 millisiemens for GM. We calculate R pi by remembering that GM R pi is equal to beta, and that turns it out to be 2.5 kilo ohms. We could also find R pi as beta times phi th over IC, which would be 100 times 25 millivolts over 1 milliamp, or 2500 ohms. It gives us the same answer. That's the basics of large signal analysis for BJTs, and doing large signal analysis lets us calculate small signal quantities. So in summary, calculate the bias point of BJT circuits by using the large signal model and a switch voltage source model of the base emitter diode. Double check that your assumption of your region of operation is correct, and you enter saturation when VCE drops below VCE sat.